advances in field theory and material science. It's a rather all-embracing subject, perhaps a bit too ambitious for its theme, hence a challenge for the speakers to follow, but it will be interesting to look forward to the emphasis that the speakers themselves set for their respective themes. As for myself, I am a bit confused about the range of topics which are supposed to be spanned between the two extremes of field theory on the one hand and material sciences on the other. But thankfully, this is a matter for the speakers concerned and led by Professor Kulshreshtha, as to how the speakers plan to combine the vastly disconnected topics coming under their respective purviews. Now, field theory has a very old subject. It has been thriving almost since the last century, that is the century that has just passed. And every development that it has been experiencing seems to have virtually no end, despite the long span of its existence. And the best references on the subject of field theory, as far as I know, is perhaps to be found in several classics, especially Feynman's lectures on physics, several volumes 1 to 8. In contrast, material science is a comparatively new discipline, roughly half a century old, not more than 50 years. And a rapidly growing one at that. Imagine, therefore, what a havoc the combination of the two, namely field theory on the one hand and material science on the other, is likely to play when experts comprising these disciplines join forces to explode on the stage. I'm afraid I may have exceeded my time limit, but I would have liked to continue, but there is a very long program, so without further trying to waste your time, I would like to stop here and look forward to listening to the speakers. Audience, and I request Professor Kulshreshtha to give this short address, which I may read out. 100 years of general relativity, black holes, neutron stars, bosonic states. So there is no need to stand in the way of Professor Kulshreshtha and the audience, and I request him to introduce this very exciting subject, 100 years of
ये आपने ये ऑडियो ले रखा है क्या?
So, ladies and gentlemen, A very, very good morning to all of you. I am very grateful to my Guruji, Professor A.M. Mitra, for his very kind words. And I would like to express my very, very sincere thanks to Professor Abhijit Nayak, Professor S.T. Chauhan, Professor Payal Mama, Professor Payal Baba ma'am, for their very kind invitation to me for presenting this talk. And I must say, Abhijit gave me a rather difficult task. So, but I am very happy to talk about this subject, and I hope I try to do some justice with the topic of the talk. So, I also would like to express my very sincere thanks to the distinguished faculty and colleagues of this great prestigious institute, Bhagwan Parasuram Institute of Technology. And with that, the title of my talk is 100 Years of General Relativity. In fact, around the world, people are celebrating the 100 years. Einstein discovered his theory in 1915. So exactly 100 years ago. And all over the world, these activities are going on. And Professor Abhijit Nayak has advised me to take up this topic, although I am personally also highly interested. So, and in this I will take you all the way to black holes, neutron stars, boson stars, wormholes, something very interesting, and eventually the time travel, the possibility of traveling in the forward time or in the backward time. All these things are very easily covered or understood, or could be understood in terms of the general theory of relativity or general relativity for short. So, this is the venue of our conference. We are meeting here at this place called Bhagwan Parasuram Institute of Technology. That is the venue of our conference. And I would like to say a few words. In particular, I would like to pay my respects to Bhagwan Parasuram. I personally have been very fond of him. Right from my childhood, I was very fond of watching Ramlila. And this particular episode of the appearance of Bhagwan Parasuram at the Sita Swayamvar was always fascinating. Always fascinating. Children like it, love it very much. In fact, he is supposed to be one of the avatars of Vishnu. And he is the connecting thread from Treta Yuga to Dwapar. From Bhagwan Ram, he appears in the Swayamvar, and eventually also he continues until Balaram and Krishna. They learn when they were a student in the Gurukul of Sandipani Rishi in Ujjaini Nagari at that time as it was called. I have visited this place personally, and B.R. Chopra Mahabharata, they also showed it. So, and he is the one to give that Sudarshan Chakra to Sri Krishna. So Bhagwan Parasuram is a symbol of Tejasvi, Ojasvi person, and I really admire his personality, so I pay my tributes to him. And then everybody is familiar with this great face, Mr. Albert Einstein, and around the world these activities are going on. Then I would like to show Gurudev Rabindranath Tagore with Mr. Einstein. Gurudev was about 18 years older than Mr. Einstein. How does it have the relevance? Gurudev has a very, very special role, special significance in my personal life, and therefore I like to pay my tributes to him. It was late spring of the year 1961. I was at the 6th standard in my school, and our school decided to celebrate the birth centenary of Gurudev in a big, huge scale. And I don't know for what reasons people somehow chose me to speak on behalf of the students, and I remember I gave almost a 1 hour talk. Like Professor Vijay Naik has given me this responsibility, it is very well connected with that. Although the talk was not written by me, my elder brother wrote the talk, and my teachers tried to create oratorial skills in me to deliver that talk consisting of several Sanskrit slokas and English phrases and idioms and poems and so on. More or less, I still remember that talk till date. And after the talk, after the end of the function, I remember that my senior students वो मुझे गोद में उठा के घूम रहे थे. So I think a teacher in Daya Shankar Kulshreshtha was born on that day, and I have very special respect for Gurudev, and my Guruji Professor Ian Mitra is present here. It's very special privilege and honor for me that he is here very enthusiastically. So then, paying respect to my gurus, we can now take off on the subject matter of the talk. Actually, this whole universe was born something like 13.7 billion years ago, and all the fundamental laws of nature were also born at the same time, 13.7 billion years ago. We are trying to understand them now, but they were born at the time of the Big Bang, when the universe was born. And these laws, fundamental laws of nature, they are mathematical in nature. So we have to appreciate this beauty of nature, and we are trying to follow it up. I would like to begin this story from Mr. Isaac Newton. You see, we would like to know these laws and these fundamental forces of nature playing around everywhere. And this is one of the human quest to understand these various forces and various laws, how to unify them, how to understand them in a simple manner. So you see, this guy Newton, he did a marvelous job. You see, falling of an apple on earth and motion of the moon in the sky, falling of an apple on earth and motion of earth or moon in the sky, these phenomenon observed at vastly different scales, at vastly different places, they are governed by the same universal law of gravitation, very simple law, that the force is m1 m2 by r square. All of us know, but I mean, this law describes these vastly different phenomena taking place in nature. And the next landmark is from James Maxwell, who discovered that electricity and magnetism, they are nothing but two different aspects of the same phenomenon called as electromagnetism. My senior friend, Professor S.D. Chauhan, is a great fan of electromagnetic field theory. So, and this is a real remarkable step achieved by Mr. Maxwell. So you can see that this very simple looking, this is the first equation, this is Gauss's law of electrostatics. Divergence of A is charge density, and this is the same law for magnetism. And if you take the right hand side to be 0, that simply says that there are no magnetic monopoles available freely. If you like to postulate one, you have to have another row of n, and you can postulate the existence of magnetic monopoles, but appropriately you have to take them into account in your theory. And this is the Faraday's law. The changing magnetic field with time gives rise to electric field. All the students at first year level, they know this. And similarly, the Ampere's law, the changing electric field gives rise to the magnetic field. And this second term, this is the contribution, the biggest contribution of Mr. Maxwell to physics. This is the conduction current, and this is the displacement. It's very easy to take divergence on both the sides. Integral of the integral on both the sides, volume integral, and they convert it into surface integral, and then you get this equation in the integral form. The same you can do with the second one. Here you take dot ds and take the surface integral on the left hand side, and you get this rate of change of the flux, magnetic flux. So that is here the rate of change of electric flux. So you can very easily obtain. And you see, these are all the laws of electricity and magnetism, and they have been combined into one form. And this actually, this led to Mr. Einstein to predict the existence of the electromagnetic waves, and they travel with the velocity of light, and they are given by the strength of the electric and magnetic forces. And now one could eventually, beyond the graduation level, one can write down the four Maxwell's equations into this kind of a symmetric form, which I have written like this: del alpha f alpha beta equal to this. So it's the covariant form, called as the covariant form of these laws. In fact, so this is for the inhomogeneous equations and this is for the homogeneous equations. And if one goes further into differential geometry, one can combine these two again further into a single equation. But the main point is this alpha, beta, etc. This really fascinated Mr. Einstein. I would like to refer when I came to Delhi University in 1971 and joined my PhD. So I had done my master's from Gwalior, and I again went to some of the important leading courses, including a field theory course by Professor Mitra. And I remember he used to write down all these things, mu, d mu, etc. And this fascinated me so much, I decided to do field theory for my whole life. And so this is now one can combine when you write. You see, because I want to cover too many things, so I would not go into the deeper details of every point. So before you write down the Maxwell's equations in the covariant form, you have to go to the special theory of relativity and talk about the covariant notations. So you can combine the special theory of relativity with quantum mechanics very successfully, and this theory is called as the quantum field theory. And this is one of the most accurate theories of nature that we have known so far, and it describes the laws of the microcosmos. I mean, so to say, a universe inside the atom. And on the other hand, so quantum mechanics, quantum field theory, it describes the world at the smaller scales, micro scales, and here is the relativity which describes physics at the macro scales. And here we have the equivalence of mass and energy. Everybody is familiar, even in the coffee houses you find this equation written, E equal to mc square, very often. So this is the mass energy, famous relation of mass and energy. So in relativity, we have the equivalence of mass and energy, and in quantum mechanics, we have the possibility of creating energy out of the vacuum. This vacuum is not empty, but is a boiling soup of particles being created and destroyed continuously. And this particular important feature of field theory, this combines very successfully special theory of relativity with quantum mechanics. Now, if we try to describe the entire spectrum of so-called physics of elementary particles, this is what is called as a standard model, which means the usual particle physics, which is known till date, and it describes the quantization of the electromagnetic field, the strong nuclear force and weak nuclear force. And this is some of the most accurately tested predictions in the physics, all of physics known so far. It has been tested accurately, and I don't know how many Nobel Prizes have gone into this direction. I will go a little bit further into this, but the point is, if this is so successful, then what are we waiting for? There is still, this theory does not include gravity into its fold, and therefore we have to, gravitational force is a very obvious force. I immediately drop something and it goes to the earth. So this is a very, very important force. So we have to try to see what happens if we try to include gravity also into the picture, and how do we, so can we combine gravity also along with these three other forces of nature which are already combined in the standard model? Can we do it? So in that direction, this is sometimes referred to as the theory of everything. A theory, if one could combine. Now, as we talked about Maxwell's equations, this is electrodynamics, this is the classical field theory of electricity and magnetism. Similarly, the classical field theory of gravity is called the general theory of relativity, or general relativity for short. And what happens here, that it is Einstein discovered or found or thought that gravity is a manifestation of the curvature of space and time. If there is no gravity, there would be no curvature, and the vice versa. So you just take a net of badminton or volleyball and you stretch it and you put a ball on it, you will find that there will be ripples in the net. You can do this very simple, everybody observes. So mass tells space how to curve, and curvature of space-time tells mass how to move. This is a remarkable observation. And you see, so when we see the motion of Earth, for example, or motion of the moon, we don't see this curvature, but this space-time becomes curved. The heavier the mass, the more and more would be the curvature. And in fact, this image describes a planet or a satellite around Earth. India is one of the leading experts in launching satellites. Not only for ourselves, we are also doing it on a commercial basis for others. I am almost a spokesperson for the Indian Space Research Organization. The TV channels, they like to catch me when there is some real major event, whether it's the Chandrayaan or Mangalyaan or something from Mars orbiter from NASA or some other activity by the European Space Organization. And you see, I would like to emphasize at this particular institute at BPIT that all these things, this is achieved with the use of high-end engineering and high-end technology. You see, even for a satellite, the curvature of space-time has to be taken into account properly. If you don't do it, you will be unsuccessful. Okay? So even for putting a satellite there, you have to take into account the curvature of space-time, and our great engineers, team of engineers and technologists around the nation, they are doing very excellent job in this direction. So now we again try to look at the we try to have to understand this particular point, that quantum mechanics and GT they are incompatible. Why? Because the scales on which they have been tested are vastly different. Quantum mechanics is tested at micro scales, and relativity is tested also in the extremely well tested theory experimentally, but it talks about macro scales, large scale structure of the universe, And quantum mechanics is relevant when these objects move around with velocities which are comparable to the velocity of light. For example, the motion of electrons inside the atom. And GTR, on the other hand, describes large distance phenomenon, physics of the solar system, neutron stars, boson stars, black holes, wormholes, universe, what and what not, or everything. And this is just a part of a section of our view, sectional view of our universe. Here, these things that you notice around, they are actually galaxies, huge galaxies. And this is obtained by Hubble ultra-deep field image. And it shows some of the most remote galaxies visible with present technology. So, technology and engineering, they go hand in hand with science. Otherwise, you cannot implement, you cannot achieve anything. So, this is an example of a high-end technology. This image shows our own mother galaxy, our home galaxy called the Milky Way galaxy. So we are being housed, our solar system lies in this very galaxy. This is an illustrative view of our solar system. See, general theory of relativity is needed to understand all these phenomena. Otherwise, you can't understand. So, this is our solar system along with all these planets. And then here, this figure shows the life cycle of a star. You see, stars can be every star, some stellar nebula, some kind of diffused activity going on in the universe, and different kinds of different sizes of stars are being formed in the nursery in the universe. And depending upon the size of these stars, they can go through a different cycle. They can become more and more massive. You can have red giants or super red giants and so on. If they there is this Professor Subramanian Chandrasekhar, S. Chandrasekhar, Nobel Indian physicist. At the young age, he has studied the subject profoundly. So if you talk about the life cycle of a star, one cannot ignore Mr. Subramanian Chandrasekhar. He set a limit that if the mass of a star exceeds 1.4 times the solar mass, then it no longer can remain stable. It will split into other objects, and that is what is happening in the this is some kind of nursery, some part of the universe where lots of stars are being born, and they go through either this route or through this route or through this route, depending upon the conditions and circumstances. You can study them with general relativity, the various detailed aspects of all these things, and depending upon the size of these stars, they accordingly end up as some, they give rise to some, for example, a planetary nebula or some supernova, or they can end up, I mean, if the death of a star is violent, then it ends up having supernova. So you have many things, but even these things are not they can eventually also go into white dwarf, red dwarf, blue dwarf, and so on, or they can eventually, by a supernova, they can go to neutron stars or black holes. So at this point, let me just say that if we have a look at a flame of a candle, for example, very simple, we just now had a lighting ceremony, you find the upper edge is reddish, and this is the coolest in the entire flame. You go a little bit further, it's yellowish, it's hotter. You go further at the center, it's bluish, it's even more hot. So the same thing holds here. So you have several kinds of these white, blue, red dwarfs. Okay, and on the other hand, so all these dwarfs, they are diffused objects, they are not compact objects. But these objects like neutron stars and black holes, they are very compact objects. They become compact because of their own gravitational collapse. So you put this hall, you put chairs and tables, fill up this hall with that, and you somehow start compressing them, they crumble onto each other, break down completely and messed up. So the whole thing can be reduced to a small thing. So these are various stages in the life of a star, and you can approximately understand them if these are the low mass stars on this side and the high mass star. So this prototype star is like our own sun, Suryadevta. So it can go via mid-sized star, then red giant, eventually becoming this planetary nebula and so on, or it can end up into this red dwarf, white dwarf, blue dwarf, etc., etc. Or it can go through this cycle, massive and supermassive and red giant, eventually giving rise to a supernova and giving rise to black holes or neutron stars. So now let us try to, because I wanted to explain these things basically to introduce the idea, because we want to proceed a little bit further. So you see, general relativity is needed to when the size of the object of mass m approaches the so-called Schwarzschild radius. What is this? I would like to explain to you. I think even the first year students knows about something called as escape velocity. So we are on our mother earth. I pick up a stone and I throw it. After some time it will fall back on earth. I again throw it with a bigger speed, higher speed. It will still fall down. But there would be a velocity called as the escape velocity. It is to be determined by this, square root of 2 gm by r. M is the mass of the object on which we are standing like earth, and r is the radius, and g is the Newton's gravitational constant. So now for earth it is 11.2 kilometers per second. If I can throw this object with this speed, then it will cross the earth's gravitational field and go away somewhere else. Now let us do a small mathematical calculation. I keep my m fixed and I want to reduce r. I can make it r by 2, r by 4, r by 10 and so on. As you reduce r, this velocity would increase and you will reach a limit that for a particular value of this r, keeping mass the same, that this escape velocity would become almost equal to the velocity of light. And I can't throw it with the velocity of light. My special theory of relativity tells me that only massless objects can move with the velocity of light, like a photon, okay, or even a graviton. But even if it has a tiny non-vanishing mass, it has to move with some velocity less than the velocity of light. So for Earth, which has a radius of something like 6,000 kilometers, if I reduce and put it in a small spherical ball with radius 8.4 millimeter, 8 millimeters or 9 millimeters, my Earth would become a black hole. It will fall back on Earth. So black hole, this is a very approximate way of understanding a black hole, which is an object from which nothing can escape, not even light can escape. So this is a very simple. Now my sun, our own sun, has a radius of something like 6 lakhs kilometer, and if I put it in the, keeping the mass same, if I put it in a ball of radius 3 kilometer, it would reduce into a black hole. So this is a very crude way of understanding. At the first level, this is how I can understand it. Now, so as I say that general relativity describes all these phenomena at vast scales, we would still like to know, when would it break down? Is there any possibility that it will break down? Yes, it will also break down at a certain point. And what is that point? That when a particle of mass, which has a Planck mass of this order or Planck length of this order, so when I talk, let us say this is very easy to understand, 10 to the power minus 33 centimeters. When I talk of such lengths, then even my celebrated general theory of relativity would also break down. And this is what we will see in our future slides. So now 10 to the power minus 33 centimeter is approximately 0, but nevertheless non-zero positive number. So we have to try to play around with figures like some kind of singularity. Also, if we run we are living here in the modern times. This is the point of Big Bang, when the universe was born, and it has evolved all through age of the universe is on this x-axis. So 13.7 billion years ago we are here. Now let us imagine that we run the universe backwards in time. What happens? We will hit upon this singularity which is called as the Big Bang. So we will end up at this singularity, Big Bang. If we run our universe backwards in time, we have to try to understand what happens around near this point. This is what we try to do. So, you see, singularities are also found inside black holes, and these are the main points. You see, this is a large star, and this is a black hole. A black hole could be maybe a million times heavier than a star, than a sun, or even more. So, the heavier this object, the more and more, the deeper the singularity, or which means the curvature of space and time becomes more and more and more and more with the increase of the mass of the object. This is what I have tried to show in this diagram, and one behind. So these are some, and supposing the black hole is rotating, then it would be accompanied by something called as some ergosphere, even the dust, whatever is there in the surroundings of the black hole, it would also rotate along with it. And so our general theory of relativity, or general relativity, describes all this physics extremely well, but when we reach here, then it breaks down, and then one needs to go further to try to understand the quantum theory of gravity, which is still in the process in the form of string theory. I will come to it in a few minutes. But before that, let us try to see a little bit further. So, gravity turns out to be a very crucial point in every consideration, and as I said, standard model describes the nature very accurately, but it doesn't contain gravity. We have to first try to see what it describes, and where it has limitations, like why does an electron have the mass that it has, or the charge that it has, is not answered by the standard model. Why are we living in 4 space-time dimensions is not being answered. So there are several things which turn out to be, even there is a black hole information paradox, because even black holes are also not eternal, they also eventually die away. What happens is that they emit some radiation called as Hawking radiation, and this radiation does not carry any information. So it seems that the information as to what once formed a black hole gets lost into the process, and this in fact led Mr. Stephen Hawking, to suggest that maybe we need to modify the laws of quantum mechanics. And one of our great friends, Samir Mathur from Ohio State University, is credited with solving this particular information paradox within the framework of the string theory. So, string theory, which includes gravity, explains many of these things. Let us try to have a rough idea about the theory without the gravity in the first place, the so-called standard model. For this, we have a look into these 4 fundamental forces of nature. If I divide the strength of them by let us say, the strength of strong nuclear interaction, so that it becomes 1, then the relative strengths are in this order: strong electromagnetic 10 to the power minus 3, weak nuclear 10 to the power minus 13, and gravitational 10 to the power minus 39. So you know why one can ignore gravitational force so easily. And this is the reason that one. So Now, what are the contents of this standard model? This describes a theory unifying the first three of them, except the last one, is that there are 12 fundamental constituents of matter, 6 quarks and 6 leptons, up, down, strain, charm, duty, tau, electron, muon, tauon, and 3 different kinds of neutrinos. I have personally, at the beginning of my career and for several years, I have worked with Professor Mitra on the relativistic quark models, and it is worthwhile to mention a little bit further on this. Just recapping the main results. So these are 12 constituents or fundamental constituents of nature. We all consist only of these things, including proton, neutron, they also consist of these things. And there are then the force carriers or the mediators of these 4 interactions. So photon for electromagnetic interactions, 8 gluons for strong interactions, W plus, W minus, G0 for electroweak theory, and eventually the Higgs particle, which is discovered recently. We can have a look at this depicted in a little bit fascinating manner: up, down, charm, strain, stop, and beauty, electron, muon, electron, electronic neutrino, muon, muonic neutrino, tau, and tauonic neutrino. These are the 12 fundamental constituents of matter. In Ramayana, we used to say Chiti Jala Pava Gagan Samira. So the 5 basic elements, and they have come down. We have come down to this level of understanding. And if you include also the force carriers, then this is the photon for the electromagnetic interactions, gluon for strong interactions, W plus minus, and V0 for the electroweak interactions. And the picture was still incomplete because there was a theoretical prediction for the existence of the Higgs scalar particle, and this has now been discovered recently at the Large Hadron Collider at CERN. And I would like to emphasize to my engineering and technology friends that all these things have been achieved. Almost each one of these things has got a Nobel Prize. I don't know how many of them, but all of them have been successful because of the availability of the high-end engineering and technology. Otherwise, you cannot do it. People in numbers, thousands and thousands of engineers and technologists are working around the globe. Nowadays, you work with this media, very advanced developed. This WWW was invented by some of our colleagues at CERN Geneva some time ago, and now it's the World Wide Web. So you can talk and chat, and so even the data is stored in the so-called virtual laboratories. You can, in all astrophysics, astronomy, everywhere you have these virtual labs. So lots of data is there. You only need some number identification to be able to access through your institute. You can do it, and you can have the data, and you can do further researches. Each one of us doesn't have to go to a particular place to do it. We can sit down in our and do it on our laptop. So now, after knowing what are these elementary particles, we also need to know how do they talk to each other, how do they interact with each other. Professor Mitra mentioned about Feynman lecture notes, and this language is called as Feynman diagrams. He is the living legend in this field. We learned our basics from him, and you describe. So this is just Compton scattering. An electron comes, photon comes, and say hello, hi, how are you doing? And if I remove this intermediate line, then this would be a classical description of the Compton scattering. But if there is an exchange particle, an electron here, then this is the quantum description of the same phenomenon. I have another process. This is an electron is going, an electron is going. One guy emits a photon, the other guy absorbs it, and this is how they talk to each other. At my even more elementary talks, I very often give an example of a girl and a boy, teenagers passing by. They stand, look at each other, smile, and they go away. There's a classical interaction. There is no exchange of a photon. But however, if they stop and exchange a letter, chitti, then that's a quantum interaction. So this is what actually happens that this guy emits a photon, this guy absorbs a photon. This is how they talk to each other. This is the quantum mechanical, quantum field theoretic language of understanding the. So this guy photon just does the job of a डाकिया, postman. डाकिया डाक लाया, चिट्ठी आती थी, लोग इंतजार करते थे. And you see, the electromagnetic interaction is still old-fashioned, so it has only one डाकिया, one photon. But electroweak theory has three, W plus W minus D0. Strong interaction is even more modern, it has 8. Now you have certain couriers, you have different courier services, SMS, email, WhatsApp, many things. So many modes of communication, not only that old-fashioned chitti. So there can be various ways you can have this interaction via the exchange of gluons. So there are 8 gluons in strong interactions, that is called as QCD process. And if one exchanges a graviton, that would be an electromagnetic interaction. That would be a gravitational interaction. But we will see, you cannot arbitrarily do, we have to see the consequences. What happens if you, I will come to this particular point in a short while, what happens if I replace my photon with a graviton? We have to wait. So, now, let me give you a very simple illustration. Let me consider 2 protons sitting at some distance apart, some distance r, and I can calculate between them using the Newton's law of force. M1 M2 by r square, I can calculate the gravitational force between them. I can also calculate the Coulomb law of force, Q1 Q2 by r square. If they are charged, then the force between them is given by the Coulomb law, Q1 Q2 by r square. And I can take the ratio of the two. So if they are stationary sitting like that, then this ratio would be 10 to the power minus 36. 10 to the power minus 36. And now what I do a thought experiment. I accelerate these 2 protons at very high speeds. And as I said, mass energy relation in E equal to mc square. Supposing I am able to accelerate it to 10 to the power 18 times its rest mass, then what will happen? The gravitational force between them would be a product of this twice, so 10 to the power 36. And if I now take the ratio of the 2, it will be 1. What does it mean? It means my gravitational force would become as strong as the electromagnetic force. The two are just comparable. The two forces are just comparable, their strengths are equal to each other. So that means I cannot ignore this force anymore, and this is how you look for the further physics beyond the standard model, and how do you at this point I would also like to point out one main difference in the Newtonian gravity versus Einstein gravity. How do we understand this? I have 2 masses, M1 and M2. They are sitting at a distance R1. I can calculate the force between them. I call it F1. This is M1 M2 by R square. Now, I change this R1 to another distance R2, bigger or small, doesn't matter. And let me call this force F2. So, everything remains same except I change my R1 to R2. Now, what happens in Newtonian gravity and what happens in Einstein gravity? In Newtonian gravity, this force F1 to F2 changes without any loss of time, in 0 amount of time, instantaneously. But Einstein says, no, it is not possible. Nothing can move faster than light. Not even the gravitational interaction. Not even the graviton, which is eventually supposed to be the force carrier of gravity. So nobody is allowed. Rule is rule, nobody is allowed to move faster. So when you change R1 to R2, force will change from F1 to F2, but in a non-zero, finite, non-zero positive amount of time to be determined by the speed of light. Because the gravitational interaction between them via the exchange of a graviton also moves with the velocity of light, not faster. So you can't change immediately R1 to R2. This is the main difference in the Newtonian gravity and the Einstein gravity. So with that we can go a little bit further. Now, let me come back to this famous diagram once again. electron scattering via the exchange of the photon. Now, I want to say, why can't I directly replace this photon by a graviton and see that there is still an electron scattering? Perhaps I can. Nothing wrong in exploring, but what happens? Let us try to understand. Here you see there is a point interaction. This vertex where three lines meet is a point vertex. This is also a point vertex. And what is the implication of this having a point vertex? The implication of this is the force is eventually given by whether it's electromagnetic force or electrostatic force, Q1, Q2 by R square, or its gravitational force, M1, M2 by R square. Both of them are inversely proportional to R square. So what happens if I set R equal to 0? The force will become infinite. Now, fortunately, for my electromagnetic interaction, there is a quantum uncertainty principle, Heisenberg uncertainty principle. And this smears out the singularity at R equal to 0 for electromagnetic interactions. However, for gravitational interaction, there is no such law, the Heisenberg uncertainty, quantum Heisenberg uncertainty principle. I say, okay, let me write one. Several years ago, I used to think, why can't I write a law? Who stops me? Yes, you can write, but you are talking about the length scale of 10 to the power minus 33 centimeters. When you talk about the scales, Planckian scale, 10 to the power minus 33 centimeters, and it's square, actually, so it doesn't make sense. And therefore, there is no way to smear out this singularity at R equal to 0 for the gravitational interaction. And actually, how do you know? I can calculate the probability of the occurrence of this process in QED, in quantum electrodynamics. This will be a finite number. There are infinities involved, but the theory is renormalizable. I have some methods to circumvent these infinities and obtain the finite result. I will not go into the details. It will need another lecture. But the other simple way is that I can spread out my vertex in space-time to avoid this singularity at R equal to 0 for the gravitational interaction. And so this is the way out. This is a point interaction. Three lines are meeting in the Feynman diagram, and this is meeting at R equal to 0. I can describe entire physics, but not gravity theory. If I have to do it for gravity theory, I have to spread out this vertex in space-time, and this is the way I should do. Then I have avoided the singularity at R equal to 0. And if I do this, then my usual particle physics interactions like electron-electron scattering or a quantum scattering in string theory, including gravity, would look like this. And this is actually a super renormalizable theory. It would look like this. Two closed strings, which are they have the length of the order of 10 to the power minus 33 centimeters. They come open or closed, they come together, they form a single string, they travel, but they again split into two, and so on. They can again meet and split, meet and split, and this is how the string-string interaction goes on. So this is what we can conclude. Now, as a result, in conclusion of my talk so far, we find that gravity is very crucial and it cannot be ignored. So we take it up further and we try to see what can be done, how do we incorporate gravity, and how do we understand things. So in this context, there are few very fundamental things like symmetries, dynamics, and geometry. These are the three main things. And I would like to give a very simple illustration. I can, for example, on this plane of table, I can draw a triangle. And I can take the sum of the three angles, inner angles of the triangle. It would be 180 degrees. Correct, Deepika? So 180 degrees is the sum of these three inner angles of a triangle. If I plot it on a plane surface, this is Euclidean geometry. Now, I take a big balloon and I again draw a triangle on this. I have not yet put any air inside. Now I have drawn only a triangle. Now I draw it out like a child, and it becomes bigger and bigger. The triangle would still be visible. Now you again take the sum of these three angles, it will not be 180 degrees. So actually we have gone from Euclidean geometry to Riemannian geometry. Where is my friend Professor S.K. Chauhan? I think he has lots of responsibilities, so he has gone. He was asking me this morning, would you go talk also about Riemannian geometry? And I promised him yes, at a very elementary level. So that means one needs to go, and so there are a few things I will show you. So one has to go from Euclidean geometry up to Riemannian geometry, but nothing is difficult. If we know the things, it's simple. If we don't know Newton's law of gravitation, it's very difficult. Okay. So similarly, there are lots of symmetries like Galilean, non-relativistic symmetries. We all understand at first year level, Lorentz non-covariant transformation, Lorentz covariant transformation. You can write down Newton's equation, you can generalize them to write Euler-Lagrange equations or Hamilton equations, and so on. One needs this, as I said, that the fundamental laws of nature are mathematical in nature, so one cannot avoid mathematics. I will not do any mathematics here, but just to give you a flavor of what one needs to do. So this I have written just Pythagoras theorem. All the students of first year know, if you have a triangle, call it dx, call it dy, call it ds. So dx square is plus dy square is dx square. This is your Pythagoras theorem that everybody knows at first year level. And I can write the same. So that means I essentially want to consider the generalizations of this theorem. Simple Pythagoras theorem of first year. I want to consider generalizations. I can write it in 3-dimensional Euclidean space. I can write it in 4-dimensional Euclidean space. Now here I want to replace w by ICT, and so dw square becomes minus c squared. I is square root of minus 1, and then this is my Pythagoras theorem in a 4-dimensional Minkowski space. So in Minkowski space, I also need to have a time axis in addition to my x, y, z. So it's very simple. I have gone from Euclidean space to Minkowski space, and if I introduce some functions a, b, c, d, which are this here I have written the same, this object dx square by dy by dx square in terms of spherical polar coordinates involving r, theta, and phi. All the students do it at first year level, but now there is a big, as Neil Armstrong said while walking on the moon, he said a small step for a man and a big leap for the mankind. It's something like that. Here, A, B, C, D are functions of t, r, theta, and phi. So this would describe a rather general Riemannian geometry. I could instead choose x, y, z, and t. So you see, this guy G mu is called as a metric tensor. If you take A, B, C, D as functions of everything, t, r, theta, phi, life really becomes very complicated. You cannot achieve much. So you try to make some simplifications to understand, make some progress. And that is what we try to do. Some of my very bright PhD students are also sitting here. This is Vivek here, Sanjeev, I can see there. The very extremely bright boys work very hard and they have mastered these things. Sanjeev has just submitted his thesis 3 months ago, working through these things and acquiring some very good results. I would just briefly mention some here for 2 minutes. So further, this is one of the special cases of the step that I showed on the last slide. On the last slide, I showed you this. Now I make a very simple case out of it. So I take this coefficient of dt square to be this, etc., etc. And then here you immediately see, if I set the coefficient of dt square to 0, which would correspond to r equal to the Schwarzschild radius. So this is actually called a Schwarzschild metric. And actually next year we are going to celebrate 100 years of this discovery of theory of black holes. obviously it's a outcome of the general relativity. So when Einstein wrote down the theory in 1915, just 1 year later, Carl Schwarzschild built up the theory of black holes, and this is the very famous kind of thing. And you obtain, so as soon as you set this coefficient equal to 0, so your black hole doesn't see the flow of time because this guy doesn't appear here. And this is called as Reisner-Nordstrom metric. So here there is charge Q also. If the object is charged, then this appears in this shape. This equation will have two roots. Here this will have only one root for R. If I equate it to 0, the coefficient of dt square, I get the Schwarzschild radius. If I equate this coefficient to 0, I will have two values for R. One of them is the event horizon and the other is the quasi horizon, etc., etc. Now both of these, they describe non-rotating object, but if you want to consider rotating object like rotating black holes or rotating neutron stars, actually in reality neutron stars can be rotating with very high speeds. I will come to it a little bit later. Then you need to go to further geometries, and so I come back for a few minutes back to the black holes. So black hole is a geometrically defined region of space-time exhibiting such a strong gravitational effect that nothing can escape from it. And the GTR predicts that a sufficiently compact mass can deform space-time to form a black hole. The boundary of this region from which nothing can come out is called the event horizon. And I think we have covered most of this, that Carl Schwarzschild 1 year later solved the equations, Einstein equation, or the equations, not only Einstein equation, it's a set of coupled nonlinear differential equations. You solve them and you find the solution. And this great friend of mine, David Finkelstein, very, very senior to me, he's an emeritus professor at Georgia Tech. I have a good record with him. He used to be editor-in-chief of a journal. And so David Finkelstein was the first one to talk about this event horizons, introducing this concept of event horizon. So approximately you can describe a black hole like some region of space, and this is the event horizon. So some imaginary surface, and nothing can escape out of it. And there is a singularity at the center, and this radius is called as the Schwarzschild radius. And this is a very nice simulated view of a black hole in front of this large Magellanic Cloud. This is actually a satellite, a small galaxy, a satellite galaxy of our own Milky Way. So you see, not every galaxy is as huge as our Milky Way. We live in Milky Way, which is huge, Andromeda, another huge. But there can be all smaller galaxies. They move around your bigger galaxies. So they are called satellite galaxies. And this LMC is a small satellite galaxy to our Milky Way. And you can see these two distorted views. And what I would like to mention here is that this is an achievement of high-end engineering. This is a simulated view. These young boys, many of you, they do such things. People like me or like Professor Mitra, they only tell you how to do things, but the people who really do it are usually young, bright people, sincere, hardworking people, and they are able to achieve. And this is another simulated view of the Large Hadron Collider. There was a lot of conversation on the TV. I also found it very difficult to convince people at that time that nothing would happen. They were repeatedly asking, "Sir, क्या कल हम सब सारी दुनिया खत्म हो जाएगी? एलएससी शुरू होगा, ब्लैक होल्स बन जाएंगे और सारी दुनिया खत्म हो जाएगी?" मैंने कहा ऐसा कुछ नहीं होगा, क्योंकि वो जो ब्लैक होल्स हैं उनकी डायमेंशन हमारे बाल से भी पतली डायमेंशन है, बहुत छोटी है. It's smaller than the thickness. So they are called micro black holes. So this is a simulated view at the LHC, again by the engineers and technologists. So this is a simulated view where micro black holes could be formed. This is another example. In fact, I am not going to the detectional aspects of this relativity, But nevertheless, a very simple illustration that supposing this is a actual star, heavier this object here, there will be more and more bending of light. This is called as gravitational lensing. There are huge laboratories around the world involving hundreds and thousands of people who are busy in trying to analyze. So you see the apparent position and the true position, and so we fall back on the massive black hole sitting at the center of the galaxy. There could be huge bending of light because of the gravitational lensing. So all these things they all require high-end technology. So this is another picture of a black hole wrapping space-time around itself. This is another black hole trying to swallow a nearby star. This is another supermassive black hole trying to swallow a star which is 300 million light years away. Let me just remind you what is a light year. Light from sun starts traveling and reaches Earth in about 8 minutes time. And if it travels for 1 hour, how much would it travel? Then if it travels for 365 days, then how long would it travel? That particular unit of distance is called as a light year. So 1 light year is that enormous amount of distance, because from sun to earth is 8 minutes. So you can estimate it on that scale, and so they can be as massive and heavy as this one is, and they can. I have not taken too many, just for illustrative purposes, and let me go to the white holes. So in black holes you have the event horizon, nothing can come out of it. A white hole is a hypothetical object which also has an event horizon, but it's other way around of the event horizon of a black hole. In black hole, nothing can come out. In white hole, nothing can go in. You see, so in that sense, it's the reverse of that. Like black holes, they have all the properties like mass, charge, angular momentum, and so on. They would also attract matter, everything, but there is no experimental observational evidence for them. So, but this is a very interesting note in this connection, that a white hole event horizon in the past becomes a black hole event horizon in the future. So any object falling towards it will eventually reach the black hole horizon, and the Hawking radiation from an ordinary black hole is then identified with the white hole emission. I will come back to it a little bit later in the context of the idea of wormholes and time travel. So I would only mention a few things about this. This is a particular stage in the cycle of a sun. If it's red giant or something, it can end up in supernova, it can end up in neutron star, for example. So neutron star is a type of compact star that can result from the gravitational collapse of a massive star after a supernova. And neutron stars are the densest and smallest stars known to exist in the universe, with a radius of only about 11 kilometers. This is very different than that of the black hole, which could be, the radius of a black hole could be even a million light years. So this is a huge difference, but they are very dense. So for example, and they can be rotating, they can have all those properties, but this is very one for at the first year level comparison. If I take two matchsticks, matches की डब्बी, एक में मैं अर्थ का रॉक भरता हूँ, एक में न्यूट्रॉन स्टार का रॉक भरता हूँ, then this match box, which is having neutron star stuff, will be 5 trillion tons of the earth rock. I mean, it is so dense. This is just the amount of this, and because when they are rotating and so on, they would create some kind of electromagnetic waves, radiation called as pulsars and so on. I would not go into most of these details. And like neutron star consists only of neutrons, you can consider the possibility of boson stars. They will consist only of bosons. So a fermion is a particle which obeys Fermi-Dirac statistics, spin 1/2, like electron, positron, neutron, proton. They all are spin 1/2 Fermi particles. But you have pi meson, gay meson, many of these particles which are spin 0. They are bosonic particles, even spin 1. So integer spin are bosons, and so they could have all these properties similar to neutron stars. And one of our students, Sanjeev, has submitted his thesis on this boson stars. Now, here I would only give an outline. So these 3 slides are just a repetition of the earlier 3 slides. What I wanted to point out here is just in a nutshell what we do. It's not only blah blah blah. There is something solid concrete behind it, how to do it. So you consider the Lagrangian density or the action of a particular theory. You can throw in here, this is an example which we have studied at the university with this bright boy Sanjeev. This is electromagnetic field, scalar field, and some potential. This is gravitational field, this cosmological constant. You solve this and you use the simple classical mechanics kind of stuff, and you can obtain this kind of equations of motion. So everybody talks about the solutions of the Einstein gravity, which actually this is the Einstein equation, but actually it's a coupled equation because this guy T mu nu has a huge structure like this. It has electromagnetic field, scalar field, everything. So, and this is Maxwell's equation. These are like Gordon equations. So this is we have 4 fields in the theory. For example, here we have 4 equations, and you can solve it further. And for example, you choose one particular potential, like Sanjeev had chosen, and you take the line element given in terms of this. So A and N are 2 gravitational fields, a replacement of the G mu field, and then those equations, they can be reduced to this. You can read these primes, double primes, and prime squared, etc. So it's a highly nonlinear theory, and it's a set of coupled nonlinear differential equations. So you can't solve them mathematically anyway, analytically, and so you solve them numerically and find the consistent, mathematically consistent solutions. And then, so we are through with this kind of a, you consider different theories. You can consider black holes, neutron stars, black holes, whatever you like, accordingly define the action of the theory. But follow the same procedure, mathematical procedure is the same. Choose appropriate boundary conditions. Now, Sanjeev and one more young boy, Vivek, sitting here, they are working together on this theory of wormhole. So we would like to see what is this wormhole. A wormhole is any compact region of space-time with a topologically simple boundary, but with a topologically non-trivial integer. The interior is different. So wormhole in principle connects extremely far distances such as billion light years or more, or for short distances such as a few feet. Then there is a large variety of them. Some of them like Schwarzschild wormholes, you can't, if you go to one side you cannot come back. So the places where you can go and even come back are called traversable wormholes. And so the simplest example, let me show you first here, then I can go back. So I can consider 2 sheets of papers. I draw some circles and I cut them, and I consider third paper, I wrap them in a cylinder. So this is the simplest example of a wormhole. So it's like a tunnel connecting 2 different space-time points. आजकल दिल्ली में भीड़ बढ़ती जा रही है, तो टनल्स बना के you can go underneath the Parliament House and come out somewhere else. So similarly, if you can, but one has to follow this path, interior path, very selectively, mathematically consistent solutions. Otherwise, you make a mistake and you die in between. So you have to follow the correct path. So these are some of the illustrations of this. That space-time here gets distorted, and you consider some kind of this kind of a situation, and this is the throat of the wormhole, and I go one diagram behind. This is, for example, so here is a black hole and here is a white hole. And this is our own solar system. We are sitting here, and this is the next nearest solar system, which is 4.4 light years ago. Alpha Centauri, which is as it is called. If you travel from here to here, you need 4.4 light years to go there. But if you follow this route via the wormhole, you can connect. So this is sometimes misleadingly referred to as the faster than the light travel. Actually, nothing can travel faster than light. But this is just a misconcept. Actually, what you do, you make a shortcut, like going under the parliament in a tunnel. Finish. Okay. So, but you have to do it correctly. So, and I thought of an even simpler example, which all of us have done at the school level. It's construction of a periscope. So you have some object here, and you put it in a submarine. You are under the sea, water, and you can see something at the top of the sea. Okay, so they are routinely commercially used by the ships and travelers in the water. But we all of us have constructed them at the school level, some kind of this periscope. But one thing to learn, this is at 45-degree mirror, this is also at 45. Now if you change these mirrors and lenses and so on, this will not work. So you have to choose them carefully. The same thing you need to do for wormholes, you have to choose them very carefully, but then you can do it. So it's mathematically possible, and general theory of relativity fully supports this idea. So there is nothing, we are not violating anything here. And then we can, this is one diagram that I would like to show. This is constructed by some young person in Germany. So computer simulated view, an example of high-end engineering. Simulated traversable wormhole that connects the square in front of the Physical Institute of the University of Tübingen in Germany with some place in Boulogne-sur-Mer in the north of France. So it opens up there. So this is a computer simulated view. Today we are talking in terms of computer. This is the Institute of Technology. Tomorrow we can have some of such things in reality too. Nobody knows. Now, you see, with this concept of wormhole, if you accelerate one of the mounts of the x of the wormhole at relativistic high speeds relative to the other, then it is possible that you can, the wormholes allow time travel, traveling in the future or in the past. It's no longer a myth. In fact, traveling into the future, not the past, via the dilation. Time dilation is a well-proven phenomenon in physics, in this simple special theory of relativity, and is routinely experienced by astronauts, but only by several milliseconds only. Traveling into the future is an experimentally confirmed fact, although by milliseconds only, and as they can check and verify it by checking the precise path against the clock that remains on the Earth. So, but the travel in the past is still a myth or a fiction, but who knows, 100 years ago, Mr. H.G. Wells wrote a very famous book, Time Machine. If I could create some aeroplane, I call it a time machine. So like my aeroplane takes me to London or New York or Chicago, my time machine may take me to backwards or forwards in time. This is idea, and British literature in particular, our ancient Indian literature is of course full of these stories everywhere in Ramayana or Mahabharata, that you travel and go back and meet there and come back and so on. So I would not go into the details of those, but even in the British literature I have found too many examples where they talk about some letters being written in 1957 and received in 1728. So there are stories. So, but so far there is no theory which stops or which forbids the backward time travel. General theory of relativity supports travel in forward as well as in backward direction, and but for giving the exact answers, there is very famous paradox here which I might like to mention before I quit. Because when you talk about the theories which allow time travel, one can create problems of causality. A very classic example is that a guy travels in the past, kills one's own grandfather, but before he himself was conceived. This is a very famous paradox. But you see, theorists also are brave people, they don't give up hopes. They say, no, we invoke some consistency principles and so on, and we can avoid such singularities. So, but anyway, the correct answer would come when we can combine quantum mechanics with general relativity in the realm of the string theory, where gravity is also taken into account, and then we can hopefully construct. I would say we live on hopes. So the only thing which has not experimentally been proven, which I have left here, is backward time travel. But we live on hopes, and there are several stories to support it. So, and general theory of relativity does not forbid the possibility of the backward time travel. I'm just through. I'm done. I'm done. At the end of my talk, I'd like to thank the organizers in particular very much for giving me this challenging task. I probably overshot my time, but as I said at the beginning, it reminded me of, if you believe me, for the last 1 week, I have been continuously working only on my talk, the way I did when I was in 6th standard for giving a talk on Gurudev Rabindranath Tagore. So that is the connection from my beginning to here. Thank you all very much for giving me for an hour.
The ideas have been presented in a seemingly simple way. The actual depth of the topics is indeed very profound. We are extremely grateful to Mr. Kulshreshtha for this wonderful talk, but I am not sure whether we have any time for discussion.
Professor Abhijit will be the best person to.
I'm not very sure about it.
A couple of minutes, couple of.
But from the younger people,
From the.
do you have some very short questions or comments? Please raise your hand.
So I have a comment to make. I mean, ask any kid about the coolest thing that they've read in this encyclopedia, it will be black hole. I mean, I still have that movie in my mind, that Interstellar, the conception of everything, and now it was so clear. I mean, I'm seriously grateful to you for telling this.
So kind of you, most welcome.
Okay.
Then Abhijit told me that the audience gave a mixed kind of audience. So I tried to work my way to make it as simpler as possible, but nevertheless not giving up on the main contents of the concepts of physics, but try to bring it down. Even if some particular level students are present, they can make out something out of it.
Okay. Are there any other questions or comments? Well, if there are not, I'd like to thank Professor Kulshreshtha for this very fascinating talk of 1 hour in which he has taken us through, not just through space, but essentially through time. And so let's thank him for very...
Actually, let me tell you the truth. I'm especially very grateful to Professor Abhijit Naik, Professor Payal Baba ma'am, and Professor H.D. Chauhan for giving me this idea कि आप एक अच्छी सी talk हमारे यहाँ ऐसे करके बनाइए. And on the top of that, when I just mentioned it to Professor Mitra, he said, "भाई मैं तुम्हारी talk सुनना चाहता हूँ ये वाली." Then I really started working on my talk. I said, if Professor Mitra is going to be there to listen to my talk, then I have to really work on it. So it made me work hard. I am grateful to all of you. I am grateful to you, sir, very much.